There you go. Okay. So 2.5, probability problems using permutations. Okay, so the goal for this one here today is to solve probability problems using counting principles for situations with equally likely outcomes. So we're going to use all of that stuff about permutations from this chapter, and we're going to apply them to probability problems. Okay. So just reading this first part here, in probabilities with many possible outcomes where order is important, it is often easier or faster to apply the counting techniques we've been learning rather than determine individual probabilities. So we can use, as a reminder, we can use the fundamental counting principle when the events are independent. We can use permutations when the events are dependent. And we can use the rule of sum when events are mutually exclusive. So as a reminder, that is the OR problem. And we can use the principle of inclusion and exclusion when events are non-mutually exclusive, which is also an OR problem, but with shared sets. Okay, and the mutually exclusive is when they are separate. So I'm going to just jump right into some examples of calculating probability. Example number 1. So in the popular dice game Yahtzee, anyone ever played Yahtzee? No? It's okay. I don't really need to know the rules. It just says here, Yahtzee occurs when you roll 5 identical numbers on a set of 5 standard dice. Okay. So part A, what is the probability of getting a Yahtzee of 6s? All 5 dice show 6 on one roll of the 5 dice. So if you individually counted them, you would be multiplying the probability of getting a 6 on each dice. And so that's 1 out of 6 for each dice roll. And if you're rolling 5 dice, then you're going to multiply it 5 times. Okay, and then your probability would be 1 over 6 to the exponent 5. But if you use the fundamental counting principle, your event is just simply getting all 6s. And how many ways are there to get all 6s is represented by n of all 6s divided by the number of elements or a number of outcomes in your sample space, so n of s. So how many ways are there to get all 6s? Well, there's only one way for all 5 dice to show up the same number. So there's only one way to get all 6s on that dice. And I'm going to divide this by the number of elements in our sample space. So if there are 5 dice and 6 outcomes for each dice, it will be 6 to the exponent 5. So this number represents 6 outcomes on each of the 5 dice. Okay, so you've been more familiar with when I showed you it was 6 times 6 times 6 times 6 times 6. So each dice roll represented the number of outcomes for each. So 6 for each dice, and then multiply them all. The number on top, that 1, well, that only represents the only way, the one and only way to get 5 6s. 5 6s. Okay. All right. So that is how I can calculate the probability using the fundamental counting principle and still get the same result as you would if you were to just do individual probabilities. Okay. Part B. What is the probability of rolling a Yahtzee of any number on one roll of the 5 dice? So the probability of getting a Yahtzee. So of any number, meaning you can get all 5 ones. All 5 of the dice could show up 2. All 5 of the dice could show up to be 3, 4, 5, or 6. So the probability would be the number of ways you can get Yahtzee divided by the number of total outcomes. Okay. Another simple calculation. The number of ways you can get Yahtzee is 6. Either all your dice rolls will turn up 1, all your dice rolls will turn up 2, 3, 4, 5, or 6. So there's 6 ways. And we already know the total number of outcomes is 6 to the exponent 5. And we can reduce, so it gives us a fraction here, and that we can reduce this fraction by dividing the top and the bottom by 6, so that I get 1 over 6 to the exponent 4. Okay, and as a decimal, that's 0.00077 And that's the probability. Okay. All right, so let's move on to something a little bit more with more restrictions in it. So dependent events. Dependent events are the events where you have conditions. Okay, one event depends on the outcome of the previous event. Okay, so here I have two brothers who enter a race with 5 friends. The racers draw straws to determine their starting positions. What is the probability that the older brother will be in lane 1 and his younger brother will be in lane 2? So in the old way of just using individual probabilities, you'd say, well, the first event is the older brother in the first position. The second event would be the younger brother in the second position, and you'd calculate their probabilities. Okay, so the probability of the older brother being in the first position would be 1 out of 7. And the 7 comes from the fact that there are 2 brothers plus 5 friends. Okay, and once the brother is placed, then the probability that the younger brother is in the second position depends on if the first or the older brother is in the first position. So instead of a number out of 7, you're now counting just 6 people left over. So you have a 1 out of 6 chance for the younger brother to be placed in the second position. And that gives me 1 out of 42. If I'm going to use the fundamental counting principle, my event A is going to be both the older and younger being placed both in the first and in the second position. So I'm treating this as one event altogether. So the probability of this event A is equal to the number of outcomes of A divided by the number of total outcomes. Okay. So in how many ways can the older brother be placed in the first position and the younger brother be placed in the second position? There's only one way. There's only one older brother and one younger brother. So there's only one way. How many total outcomes are there? Well, that is a permutation. Okay, that's a permutation. Remember, so you have 7 people altogether, but how many ways can you place people in the first and second position? So it's a permutation of 7p2. So basically arranging the first 2 spots from 7 people to choose from. Okay, so I'm going to write here as a note, 1 represents the only one way, only one way this can happen, having the older brother in the first and the younger brother in the second spot. And 7p2 represents the number of ways 2 of 7 racers can be placed. Okay, and once you calculate the permutation, you'd get 1 out of 42. So the probabilities are 1 out of 42 chance for the older brother and the younger brother to be placed in the first and second spot. Okay, flip the page. Let's look at another one here without replacement. So this is an example, again, of a dependent event. So a bag contains 4 red, 3 green, and 5 blue marbles. 3 marbles are drawn, 1 at a time without replacement. Just like the checkers, the red and black, or the red and white, or the black and white checkers placed in the bag example I did a while ago. So you're not replacing them anymore. Once you take them out, they stay out. Determine the probability that the order in which they are selected is red, green, and then blue. So under the individual probabilities, you'd calculate first the probability of drawing a red. So you have 4 red out of 12 marbles in total. After you draw the red, you don't replace. So you're left with 11 left over. So what's the probability next to drawing a green, given that you've drawn a red? It would be 3 out of 11. Times the probability you draw a blue, given that you've already drawn a red and a green. That leaves you 5 choices out of 10. So these numbers are decreasing by 1 because you're not replacing the marble, and these numbers come from the numbers that you see up here. Okay, and that would give me 4.5%. Now, if you are doing this using our counting technique. So we're looking at the probability of getting a red, green, and blue in that order. It would be the number of ways you can get a red, green, and a blue in that order divided by the total number of possible ways of drawing 3 marbles. So again, this is a permutation problem. Just think about if I'm drawing one marble, that first marble, how many ways can I arrange that first spot given that I have 4 red? Well, that's just simply 4p1. And that one spot, the first drawn marble, chosen from 4 red marbles. Then I'm going to multiply that with my second drawing of a marble. So I'm drawing the second marble, so I have to choose 1 marble. From how many? Well, if I'm hoping to get a green one, I have 3 green to choose from. So 3p1. After I draw that marble, I have a third marble to draw. So how many ways can I draw the blue marble? Well, there's one marble I'm drawing, and there's 5 ways I can draw the blue marble. 5 items to choose from. It's 5p1. And I divide by the total number of possible outcomes. So what are the possible outcomes? Well, the whole problem is about me drawing 3 marbles. So I'm finding the arrangements of 3 items given how many marbles in total? 12. 4 plus 3 plus 5 make 12. So I have 12 marbles and I'm choosing 3. I'm arranging 3 of them. So that's how I set up the problem using permutations. So if I solve this, I get, you have to enter this into the calculator, so it would be 60 divided by 1320. So I'm just skipping the steps and putting the final answer there, which is 0.045 repeating, or 4.5%. So 4.5% chance that when I draw 3 marbles in a row, I get exactly red, green, and blue in that order. Blue, green, green. Same idea. Probability of getting a blue. Well, 5 out of 12 marbles. 5 blue out of 12 marbles in total. Then after I draw a blue, I'm down to 11 marbles. 3 of them are green, so I have a 3 out of 11 chance for green. And then after I draw 1 green, I'm down to 10 marbles. But I'm also down to 2 green marbles left in my bag, so I have a 2 out of 10 chance for a second green marble. So my probability here is 2.3%. Using my counting techniques, probability of getting a blue, green, green, and that order is my event, which is the number of ways to get a blue, green, and green in that order, divided by the total number of ways that you can draw 3 marbles. So the probability of drawing a blue, I'm just drawing 1 from 5 items, times the permutation of drawing 1 from, sorry, not 1, we're drawing 2. So we're drawing 2 green marbles. So you want to draw 2 green marbles from 3 possible ways to do it. So 3 permutation 2 divided by 12p3 again. Do I have my calculator here? So let me see if I can do the individual ones. So 5p1, 5 permutation 1 equals 5 times 3 permutation 2, which is 6, divided by 12p3, which is 1320. So that's equal to 30 over 1320, or 2.27%. Blue, blue, red. So same idea. Probability of blue, blue, red is the number of ways I can get blue, blue, red in that order, divided by the number of total outcomes of drawing 3 marbles. So if I'm looking at drawing 2 blues in a row, then I'm trying to arrange two marbles from a total number of 5 blue marbles, multiplied by the number of ways to pick my third marble from a set of 4 red marbles, 4p1, divided by the total number of outcomes, which is 12p3. Okay, and that's going to equal 80 out of 1320, which is 0.0 0.06, repeating, or 6.1%. Okay, so that is dependent events. Next part is mutually exclusive events. So Yasmin draws 3 cards in order without replacement from a standard deck of cards. Is the probability that all 3 cards, or what is the probability that all 3 cards are kings, or that all 3 cards are queens? So I'm interested in the probability of having 3 kings or 3 queens. Okay, so this is an or problem. Again, this is why we're doing mutually exclusive events. So they're separate. Remember, they are separate. Think of the diagram that has 2 separate sets. So I can draw my first event 3 kings or drawing 3 queens. So individually, I'm looking at the probability of drawing 3 kings, and I'm adding it to the probability of drawing 3 queens. So I asked the question, well, how many ways are there to draw 3 kings? So you have to draw 3 cards, right? So you're going to draw, it's a permutation problem. So I'm arranging 3 cards from a choice of 4 kings, plus I am, so for the queens, the probability of getting 3 queens, well, I am drawing 3 cards from a choice of 4 queens, and I'm dividing it by the total number of outcomes because we're drawing from a standard deck of cards. We're drawing 3 cards from a choice of 52 in total. So I'm dividing it by the total number of outcomes. Okay. And so I have here, let's go up here, 48 ways to draw, well, let's say 24. So 24 ways to draw 3 kings plus 24 ways to draw 3 queens divided by 132,600 ways to deal or to arrange 3 cards when you have a standard deck of 52. And that is 0.036%. A very low probability of drawing either 3 kings or 3 queens. Okay, a problem like this might come up when you're playing poker. Okay, poker hands often have something called a full house, and a full house requires you to have 3 of a kind. So either 3 kings, 3 queens would often make among the highest valued hands. Okay, non-mutually exclusive events. So Min draws 5 cards in order without replacement from a standard deck of cards. What is the probability that all 5 cards are face cards or red cards? So now this is non-mutual because remember that diagram, you have some overlap. Some of your red cards can be face cards, okay, and vice versa. So what I'm looking for is the probability of drawing a face card or a red card. And using that non-mutually exclusive formula, you're looking at the probability of drawing a face card plus the probability of drawing a red card minus the intersection, probability of a face card and a red card. Okay. But remember back in chapter 1 when we did these probabilities, it was all about drawing 1 card. So it's easy to say the probability of drawing a face card. Well, how many face cards are there in the deck? There are 12 of them, so you normally would say, well, 12 out of 52. But I'm not just drawing 1 card; I'm drawing 5 cards. Okay, and that's why this is now a permutation problem because of this number here. We're trying to arrange 5 cards. So I'm interested in finding the arrangement of 5 cards given 12 face cards, plus we're drawing 5 cards given a set of how many red cards do we have? So we have 26 red cards, so 13 diamonds, 13 hearts, minus the intersection of the 2. So you have to kind of do a little bit of counting. What are the red and face cards? So we have the Jack, Queen, King of Hearts, and Jack, Queen, King of Diamonds. So we have 6 to choose from. So we're looking at arranging 5 cards from a set of 6. Okay, and then we divide that by the total number of outcomes. So So we have, remember, we're still arranging 5 cards from a deck of 52, 5 cards from a deck of 52, and 5 cards from a deck of 52. So the top part says, for the first term, so drawing 5 cards, probability is the permutation of arranging 5 cards from a set of 12 face cards divided by the total number of ways you could be given 5 cards from a deck of 52. That's how I'm calculating the probability. Okay, so we have some fairly big numbers here. I'm just going to write them down. So 360,000, 360 ways to draw to arrange 5 cards from a set of face cards. There are 7,893,600 ways to arrange 5 cards from a set of 26 red cards, and I subtract 720 ways to arrange 5 cards from a set of 6 red face cards. And the total number of ways to arrange 5 cards from a deck of 52 is 311,875,200. That bottom number there is quite significant. This tells me that's how many possible poker hands you can have in a game of poker when you're dealing 5 cards in a set of 52. So 311 million possibilities. Overall, when you add them all up, I get 48. Sorry, I'm not saying 48. I get 8,253,240 over 311,875,200, which is equal to 2.6%. So the 2.6% chance that all 5 cards will either be red or will be face cards. Yeah. 7 million instead of 8 million? So if I add, are these, do you get these 3 numbers? Oh, you did them all at the same time? Can you show me your calculator? 12p5 is 26p5 minus 6p5. Let me see if this is. You're right. Good question. I'm not sure why it's 7,987,000. Maybe here. Let me see. Let me double check one more time. 12p5 plus 26p5 minus 6p5. 7,980,000. I think you're right. Okay, so let me cross that out. 311,875,200. So that should change to. Oh, it's still 2.6%. So maybe I just wrote down the wrong number. I had recorded the wrong number here for my notes. So that should say. Oh, I lost it. Times. Okay, what was it? 7 million. Okay, that's fine. Okay, but still 2.6%. All right, example number 6. 4 students, 1 from each grades 9, 10, 11, and 12, line up to pose for a photograph. What is the probability that they will be in order of their grades? So the probability of the event 9, 10, 11, 12 in that order. Okay, and that's equal to the number of ways you can arrange 9, 10, 11, and 12 divided by the total number of ways. So there's just one arrangement of getting these 4 students in the order that we want them in. How many ways are there to arrange the students? Well, there are 4 factorial ways. And that's can be said as 1 over 24. Okay, and remember 4 factorial is just simply saying 4p4. Okay, so 1 over 24 or 0.0417, 4% probability of 4.2% probability of them lining up in the order of their grade. Part B, what is the probability that the grade 9 and 10 student will not be beside one another? So when it comes to these kinds of restrictions, helpful to draw a picture. So here are the 4 students. We do not want the grade 9 and 10 student to be beside each other. Well, maybe because they're, I don't know, they hate each other or something. Who knows? So this is the situation where you're going to use a kind of indirect method. So I'm going to find the number of ways you can put them together, the 2 factorial ways to put them together. If treated as one unit, then there are a total of 3 factorial ways to arrange your 3 units, the first unit, second unit, and the third unit. And so I'm going to start by looking at the probability that they're not together being equal to 1 minus the probability that they are together, because it's easier to calculate the probability that they are together. So the probability that they are together is going to be equal to 1 minus. So the probability that they are together, it's how many ways to arrange them? 3 factorial times 2 factorial ways, divided by the total number of ways to arrange these 4 students, which is 4 factorial. And that's equal to 1 minus 12 over 24, or 1/2, or 50%. So there's a 50% probability of that the grade 9 and 10 student will not be beside each other. So example number 7. Oh, birthday problem. Classic problem in probability. So from a group of 16 people, we started off the class with 16 people, so this would have been perfect if everyone was still in the class. So from a group of 16 people, what is the probability that none will share a birthday? Okay, I'm gonna fill in something with our notes and then I'm gonna explain. So first of all, you'd look at probability that all are different. Probability that all the people have a different birthday equals the number of ways we can all have a different birthday divided by the total number. Okay, so n of s. So it's important to note here that this is where outcomes are dependent on each other. Outcomes are dependent. I don't know why my writing thing is not dependent or dependent. Okay, let me just save that there. All right, so there we go. So what is the number of ways that they can all be different? Well, to do that, I'm just gonna open up a OneNote file here, and let's just go down to a new page. Here we go. So let's just look at counting it individually. So we have the first person. The first person you have 365 days in the year. So that first person could have any one of those 365 days. Then you have the second person. This is the first person. Then you have the second person. The second person, again, there are 365 days in the year, but after the first person has their birthday, you cannot count that anymore. If the second person has to have a different birthday, then you only have 364 days left of the year to choose from. Okay. For the third person, same idea. Once you have the birthdays of the first two, if the third person must have a different one, then you're now limited to 363 possible outcomes out of 365. And then for the fourth person, same idea. There are only 362 outcomes out of 365 if they all have to have a different birthday. And if you keep going, you'll get to the 15th person, which is 350 divided by 365. Okay, so that's how you should look at the ways that you can have in terms of the number of outcomes for making sure each person has a different birthday. But all this is just the permutation, P. The ways to choose to arrange 16 people from a set of 365 days of the year. Okay? And you divide that by 365 days of the year to the power of 16 as the total number of ways of arranging to have a birthday, whether or not some people have the same birthday or not. So that's the total number of outcomes. We also learned how to express this back earlier in the chapter as using factorials, right? So this would be 365 factorial divided by 365 minus 16 factorial. Okay, and this would be, oh, where is my, why can't I move the screen? I don't know. Okay, so this would be 365 factorial over 349 factorial. So you can use the factorials this way to also come up with the same result. So let me go back to my, my note here so we can finish filling this in. So the number of ways that they can all have a different birthday is 16 arrangements out of from a possible 365 days divided by all the possibilities of having 16 people and their birthdays. Okay. And so this first part here, just to have this complete in your notes, it's going to say no two birthdays are on the same day. No two birthdays are on the same day. And the second part here, down at the bottom, this is each of the 16 people having, how did this turn into a smiley face? Day. There you go. Each of the 16 people having a birthday on one of a possible 365 days. So the bottom part counts all the possible outcomes, even if you have multiple people with the same birthday. Okay. The top part only counts the arrangement of 16 people having individual birthdays, unique birthdays. So if I divide these two numbers, let me do this on the calculator to make sure I have this right. So 365 P16 divided by 365 to the power of 16 is 0.716 or 71.6% chance. So there's a 71.6% chance that out of a group of 16 people, no one will have the same birthday. Everyone will have a different birthday. What about in our class? You can do the same thing. How many people do we have here? 1, 2, 3, 4, 5, 6, 7. So if we have 7 students in this classroom, maybe we'll say 8 if you want to include me. So the number of ways you can arrange 8 people's birthdays from having 365 to choose from divided by 365 to the exponent 8, that will tell you the probability of everyone here in this room having a different birthday. Okay. Part B, what is the probability of them sharing, at least 2 of them sharing the same birthday? So the probability of at least 2 sharing the same birthday is equal to 1 minus the probability of them being all different. Okay. Now I hope that logically makes sense. Think about that for a moment. You might, automatically the first question you might think of, well, why isn't it, well, how could it be that way? Why didn't you say at least 1 would be 1 minus P of all the different? Well, that wouldn't make any sense because you can't say at least 1 person has the same birthday as 1 person. You have to have at least 2 people to count these kind of questions. You have to have a pair of people to compare. So the probability at least 2 people share the same birthday would be every other possibility than them being all different. So that's why it's 1 minus the probability of all of them being different. And that's just 1 minus 0.716, which is 0.2836 or 28.4%. So therefore, there is a 28.4% chance that at least 2 of the 16 share the same birthday. Okay.